Welcome back to Lecture 5 of a series on molecular simulations and statistical mechanics. In this lecture, last time, we left off by studying the Lagrange equation of motion. We were able to derive this directly from the definition of the Lagrangian and the action, along with Hamilton's principle. In this lecture, we're going to look at some conservation laws and symmetries in systems. And symmetry. So we're really this lecture will be quite short. We're just going to introduce how we can use the Lagrangian to start to understand conservation laws with respect to things like linear momentum, angular momentum, and energy. So to begin, we want to re-emphasize that as a mechanical system evolves in time and space, there are specific quantities that remain constant. There are certain quantities that remain constant. These quantities are called constants of motion. Constants of motion. You may have also heard them called conserved quantities. Now, why do we care about conserved quantities? Well, first they're going to let us understand our system better. We're going to be able to keep track of very specific changes in time. For instance, if we're running a molecular simulation and we're not conserving energy in a system that should be, we may realize that we're not at equilibrium, or we're not actually running the appropriate simulation and need to change something, right? So it can give us sort of this intuition for how systems evolve in time, and also give us a way to check ourselves if we're doing something wrong. So the first quantity that I want to discuss is the conservation of linear momentum. And the way we're going to get to this is by looking at the Lagrangian of a system and a perturbed system, or a translated system. So let's consider a mechanical system A consisting of n particles. So we have a mechanical system here, and it has, let's say, n particles. I'll just briefly draw them. You get your n particles. And this system is described by a Lagrangian, LA, which is going to be equal to some function of all the positions, all the velocities, which you remember I put a dot for the velocities, and time. Now, let's make an identical copy of A, except this time what we're going to do is we're going to move that copy in space by a specific vector. So we're going to take every single particle, and we're going to move it by the same vector. So this is a translation. And we're going to call this vector delta r. So we're going to take everything and we're going to add delta r to it. Okay, well, all that means is that our positions now, so in our original system, our positions were just at Ri. But now in our new system, the positions are at Ri plus delta r. Well, let's write the Lagrangian for this. In our new system, LB, this is going to equal L, Ri, R1 plus delta R, comma, Rn plus delta R, comma, R1 dot. The delta R doesn't change the velocity, so we just have the exact same thing that we had before here in the velocity part. Rn dot and time. Now my question is what's the difference between LB and LA, right? At first glance, they have the same velocities, they just only have a perturbed position, but could we write some sort of relation between LA and LB? I'll stick to my color scheme here. What could we say about these guys? Well, it's reasonable to assume that if these systems are far enough apart, if this delta R is far enough away, and these systems aren't interacting with each other, that these should probably be the same thing, right? Now, that's kind of interesting to think about, like, is that actually true? And of course, it depends, right? If you're in an external field like gravity, right, and gravity's pointing, let's say, in this direction, and you move things up, you've all of a sudden changed the potential energy, and you have changed the Lagrangian. But in the absence of an external field, so nowhere that being in a different point in space doesn't influence the equation of motion, then it seems reasonable, right? Like if I ran an experiment on some particles moving around in this room, and then I went into another area of the world and ran the same experiment, I should expect to get the same results. In other words, these Lagrangians should be the same. So this is referred to, this concept is referred to as the homogeneity of space. And you might think of it as, well, here is as good as anywhere to run this experiment. And of course, that's only true when you don't have this external field or this spatial component where translating it will actually change the Lagrangian. Now, we could also refer to this, this relation here as translational invariance. So the Lagrangian is invariant to translation. Translational invariance. So let's look at the consequences of this, particularly with respect to a differential change in R. All right, so we had our system A and a system B. And we said that the homogeneity of space would give us that LB is equal to LA. So now let's consider if instead of perturbing by a delta R, so instead of going from A to B by adding delta R to everything, let's add a very small perturbation, some infinitesimal delta R. Well, what does that give us? Well, in our Lagrangian for system B, we're now going to have R1 plus delta R, Rn plus delta R, R1 dot Rn dot T. And I'm going to move this guy to the other side by subtracting it on each side. So minus L, our original system. And it may seem pedantic to write out all these dependencies, but you'll see why these become important. And of course, if we move this to the other side, it equals 0, right? So we have this difference. Now, you're probably seeing a theme in this course. What we have here is actually something that we can write as in terms of a Taylor expansion, right? Because we have arguments with some infinitesimal perturbation minus the same arguments. So it kind of looks like a derivative. So to the first order, we can write this as a sum, because we have to go over every single variable, as a sum of the partial L, partial Ri's. And this will go from I equals 1 to n times delta R plus these higher order terms that we are leaving out. So once again, this is the linear approximation. Linear approximation, or a Taylor series, or a Taylor expansion of order 1. So this difference can be expressed in this way through the Taylor series. Now, there's a quantity here which we can relate through the Lagrange equation of motion to another quantity, right? If you recall the Lagrange equation of motion was d dt partial L partial Ri dot, right, minus partial L partial Ri equals 0. So we can move this guy to the other side. That guy is right here, so we're going to substitute in this one. So this is just going to be equal to, now, the sum, I equal 1, of d dt of partial L partial Ri dot d delta R, and we're going to ignore the higher order term. All right, well, let's think about what this guy is, this partial L partial Ri dot. Partial L partial Ri dot. Can we write this in terms of the momentum? So we want to get this into a form where we can start to look at these conservation laws, right? So this guy's equal to 0. And kind of, like, I guess before we get into that, where we're going with this, right? We could multiply this dr by each side because it's a constant with respect to this sum. The ddt is a linear operator. We can pull it out, and what we can get is that 0 equals this sum, where 0 equals d dt, the time derivative, of the sum of partial L partial Ri dot over the whole system. Well, that means that this sum is a constant of motion because it's not changing in time. The derivative is 0, right? So let's think about if we could write this in relation to some other quantity. Well, recall partial Ri, or partial L partial Ri dot, is just equal to the momentum. So we can write this. This was a definition, but remember we showed earlier how it made sense that this was the definition. So now we can rewrite this as 0 equals the time derivative of the sum of the momenta, of all the pi's. Well, the sum of the pi's, we usually would call this the total linear momentum. And what that shows, if we define the total linear momentum, which is usually denoted by big P, that the time derivative of the total linear momentum is 0. In other words, d dt of P equals 0. This implies that P is a constant of motion. So total linear momentum is a conserved quantity. We've just seen that the conservation of total linear momentum holds when there's no external field. The same, and I will not do the proof, but the same holds for the angular momentum. So for angular momentum, it will be a conserved quantity. And the way that you would do the proof is if you had some initial Lagrangian for your system, and let's draw one of the points. So we'll have your origin extending out to a point in space by some vector, right? The way that you do this proof is you instead of translating the system by a delta r, you rotate the system in space along an axis. So if this is the axis phi that you're rotating around, you're going to take the vector and rotate it some direction. And it's going to move your new point by some distance. I want red here. Delta r, which is a function of how much you rotated it, so some delta phi around the axis, right? And then, of course, you have some angle between phi, the axis phi, and Ri. And so by keeping track of the geometry of this system, we're just going to rotate every point in space and then rewrite the Lagrangians again. And we're going to do LB, and of course this is going to be our perturbed system, so we're going to have our R1 plus our delta R, whatever we calculate here. And in this case, it's going to be a function of theta and phi, because there's rotations, right? Plus dot dot dot, as usual, Rn plus delta R, rotated in space, and the velocities in time. And we're going to subtract LA. And just as before, we're going to do a Taylor expansion to the first order. And within this Taylor expansion, we're actually going to find a quantity that gives the cross product between Ri and d phi. And this cross product is defined as the angular momentum. Because of the Taylor series expansion, we're going to have a summation over everything just as before. And to get the exact form of it, what you're going to end up with at the end of the math is something that looks like this. You're going to have your d phi of Ri cross Pi plus Ri dot cross Pi in your Taylor series expansion. And of course, this can just be written as being equal to the sum delta phi sum of Ri cross Pi only. And the reason for this is because the velocity and the momentum are in the same direction, so their cross product will be 0. You'll end up with just this quantity, which is defined as the summation. And we have a time derivative in here that I forgot. So just as before, we're going to have that time derivative coming through all of it. This is really sloppy, so let's bounce it up here to where we're going to have 0, because we're assuming that, just as before, rotating it doesn't impact the Lagrangian. We're going to have 0 delta phi is equal to d dt summation over the cross product between our initial vector and the momentum. Well, this summation over all the particles is the total angular momentum. We call that m usually. It works for any delta phi, so 0 is equal to d dt, the sum, and or d dt of the total angular momentum m. And so we say m is a conserved quantity. So just not going through the math because it's very similar to the linear momentum case, except there's some trickiness in keeping track of all of the angular dependence of the system. The last quantity that we want to talk about is energy, and look at the conservation of energy in the picture of this Lagrangian. So let's consider our system again. R1 dot, Rn dot, T. Now, L depends on time explicitly here, right? We've explicitly given it a time dependence. but it also depends on time implicitly through its coordinates, because the coordinates change in time. So technically, each of these guys are functions of time. When a function depends on something directly in its arguments, that's called explicit time dependence. So L does have explicit time dependence in a general sense. When you have a variable that depends on time as an argument, this is implicit time dependence. And the Lagrangian has both. So let's try to take the time derivative of L, d dt of L. Well, what does that equal? Well, if we have this general functional form, we need to keep track of all of the variables and all the time dependencies. And because these are functions of time, we're going to have to implement the chain rule. So in general, dl dt is going to be a sum over all the positions of partial L, partial Ri, right? We're just doing the chain rule, so we're doing partial L, partial Ri, times partial Ri, partial T. Plus, now we have all the velocity dependencies, which of course are also functions of time. Partial L, partial Ri dot times partial Ri dot partial T. And of course we have the explicit time dependence, so plus partial L partial T. So this is the time derivative of L. Well, let's simplify this a little bit, because for instance, we know partial R partial T is the velocity, or Ri dot, right? So let's rewrite this now as being equal to the sum n I equal 1. And we'll combine the terms here because this is over the same summation. Partial L partial Ri times Ri dot, it's this guy, plus partial L partial Ri dot, partial Ri dot partial T is just, we could write as Ri double dot, right? The second derivative. Plus partial L partial T. Partial T. Now, we're going to rewrite this term, because if you notice, this looks like it could be the result of a product rule of a derivative in time. So let's consolidate everything. So this is going to be equal, we're specifically looking at this term, to the sum over all the particles. And I'm going to argue that this is equal to the sum of d dt of the product of partial L partial Ri dot times Ri dot plus partial L partial T. All right, let's check ourselves. d dt partial L partial Ri dot times Ri dot, well, that's just going to give you d dt partial L partial Ri dot times Ri dot plus partial L partial Ri dot times Ri double dot. Does this look like that equation? Well, recall that partial L partial Ri through the Lagrange equation of motion is just equal to d dt partial L partial Ri dot. Considering that, we have this term here times this term plus this term times Ri double dot here. So that checks out. So this form works here. I've rewritten the result that we just derived. And now what I'm going to do is I'm going to take all of these terms and I'm going to combine them under this d dt. Now before I do that, I want to make an assumption here. And this is a really important assumption. We're going to assume that our partial L partial t does not depend on time. So this equation here is quite general. But now we're going to say, okay, if the Lagrangian is not explicitly dependent on time, then this term is 0. If that's the case, then what we can do is we can subtract the dl dt on both sides, pull the d dt out because it's a linear continuous operator, d dt of the sum over all of the partial L partial Ri dots minus L equals 0. And remember, for no explicit time dependence. In other words, partial L partial t is 0. Now, what is this quantity? Well, if you recall from a previous lecture, we defined this as the energy function, h. This means that this energy function is a constant of motion because its time derivative is 0 for no explicit time dependence in a Lagrangian. Furthermore, if there is no explicit time dependence, this h is equal to the total energy of the system. And this implies that energy is a constant of motion. Now, an interesting interpretation of this, right? In linear and angular momentum, we invoked the concept of translational invariance or the homogeneity of space. But we can actually interpret this result in a similar way, but with respect to time. So essentially, all we've done here is by taking this time derivative of the Lagrangian, we've said, oh, the Lagrangian going from one time to another requires that the energy stay conserved, right? So an interesting interpretation is that the conservation of energy is a result of the homogeneity of time. You might say running the experiment now is as good as running the experiment later. Any time is as good as any other time. Thank you guys so much for tuning into this lecture. This is a shorter one on the conservation laws. But next time we're going to get into Hamiltonian mechanics and really the final stage of classical mechanics that we need to start breaking into statistical mechanics.